Okay, that's 45 exactly, and we continue our session. The next speaker is Professor Pavel Krapivsky from Boston University and from also from Santa Fe Institute. Pavel Krapivsky is a specialist in non-equilibrium statistical physics and in stochastic processes in physics, chemistry, and biology. So, please, Professor Krapivsky, your voice.
Hello, everybody. Thanks a lot for this invitation. I got to know about this wonderful thing which you guys organized a little less than half a year ago in Paris, where I met Yuri. And Yuri gave the very interesting colloquium about Ising or Ising. He told us many bits about him. For instance, you think how to pronounce him. Obviously, Ising originally, but he somehow changed some of his pronunciation, some name a little bit when he moved to US. Anyway, so when he asked me, to give this, of course, I was quite excited to say the least, but, I was sure that I will talk about actually Ising model. And there is something in this Ising or Ising model, which I worked with some of my friends for many years, which is, totally kind of puzzling. And still, very little knowledge is required. You just consider Ising model at zero temperature and with some dynamics. And so I guess Ising could have been able to understand definitely, because it was really very, very basic setting, but then results very non-trivial. But unfortunately, we don't have much progress about it. Still very, very beautiful thing, and maybe one day, I hope, if I come personally to Lviv, maybe I'll describe it. And so I'm going to talk today about even more basic problem, I would say. Basic in a sense that it requires really almost, at least formally, knowledge from middle school, high school at best. Yeah, so I will be talking about just a collection of balls. And balls are totally ideal. They just collide according to the laws of classical physics. And the most simple laws, just elastic collisions. They do not rotate, they just collide. Yeah. And so that started essentially with when I was talking with my friend Sid Redner. For quite some time, we were just, playing a little bit around, because mathematicians have great developments in this billiards. And we were just, trying to really a little bit to understand what they're doing. Yeah, and for instance, that's actually a field which is, the most simple imaginable question you ask, and there are no answers very often. For instance, imagine that you are in three-dimensional space. You have two identical balls. How many times they can collide? Yeah, you think for a second and you say one. That's true. At most one, and then they just separate forever. If you have two balls, if you have three balls, to find the maximal possible number of collisions is extremely hard. So two people did it in about 30 years ago, and this number is equal to 4. Nobody, I guess, truly checked the proof quite long, but they are good people, strong scientists, so we trust it. And generally, so nobody knows the answer for instance, if the number of balls is 4. So I return to that problem at the end, a little bit return, but basically talking about that problem, about some other problems, we somehow not decided, it was clear that it's very hard to compete, with mathematicians in billiards, what kind of billiards they consider, which involves a finite number of balls. And so we thought, why don't to consider infinitely many balls? And that's quite much closer to statistical physics. And so that's what I've done first work in 2008, so very long time ago, with Sid Redner, with whom we sort of really chat about those billiards for years, and Tibor Antal, another friend of mine. And then, okay, then people worked on it a bit, quite a bit. And then maybe in 2020 or 21, Abhishek Dar wrote to me, and so he sent some their work. And so somehow I joined them. I started, so we wrote a few more papers. And also there are a few which are in progress, or at least I think about it. And actually I would really try to focus my talk more on unsolved things than on solved things. Okay, so what is the problem? The problem is the following. So imagine that you have infinitely many particles, and really the simplest case, particles are just spheres, elastic, everything, and they're stationary. So that's what we call cold gas. And then imagine that, for instance, you just kick one of those particles, and so you get a picture which shown on the left. So the red balls are those which are moving, and the blue balls those which are still stationary. The red balls, okay, disks here in 2D. These disks, their size a little bit increased just for visual purposes, but they are small, the same size as the blue ones. And so you see this region where balls are moving is growing. And okay, there is also another picture which we call splash. It's on the right. So initially half space, okay, here half plane is occupied. And we just pick up like in billiard, but in billiard you typically have finite number, but we have just pick up one on the left and just kick it orthogonally. And then we see what's going on. And so what's going on is presented here. And somehow you would like to understand such pictures. And maybe it's harder to understand than it is, the picture on the right, but on the left, at least there is some kind of understanding. And so that's what we were doing in that paper in 2008. And just using some scaling argument simulations, all sorts of available tools. For instance, we found that this region on the left, it's asymptotically seems to be spherical, and it's growing with time as square root of t. And then we found some other things, for instance, estimated total number of collisions up to time t and so on. And then, at the end, already before submitting, somehow it just occurred to me that if you do the same, but not in 2 dimensions as on this figure, but in 3 dimensions, so in 3 dimensions, you get that the power with which it expands is t to the 2/5. And that's exactly what I learned as a student, what was, kind of so-called strong explosion. So-called, strong explosion, which was studied in hydrodynamics in like mid-40s to mimic atomic explosion, actually. Okay, so anyway, so what is now more formal? What's our system? The simplest one, at least on the left, which I showed here on the left. So we have, hard spheres, initially at rest, distributed uniformly throughout the entire space. And we kick one, particle, one sphere, and just we see the outcome. So that's high school framework was apparently first studied this in this our paper in 2008. Then, for instance, some other groups.
Pavel, excuse me, about questions, we did not fix this at the beginning. Is it possible to interrupt you with a question?
Absolutely.
Then may I use this possibility right now?
Yep.
What do you mean uniformly distributed?
Well, it means that you for instance drop these balls without any correlations. You drop with a given density. But for if you do it, of course, balls can't overlap. So, for instance, I don't know, if you overlap, you move them a little bit. So it's just mathematical. If, for instance, you have bigger and bigger size, the number of balls would be more and more close to the volume times the density.
So a kind of Poisson distribution, right?
Yeah, it's uniform. Yeah, it's better to have, for instance, than if you put them on a lattice, on the lattice grid. In that case, it's a lot of correlations. It's not so good. Yeah, it's better to consider truly uniform distribution. Yeah, so totally without correlation. But of course, there is one thing. Okay, our spheres are typically very small. They occupy little volume of the space. They hot spheres. They can't overlap. And when they start moving, some of them, whenever they hit each other, they just reflect from scatter using the laws of elastic collisions. So they do not feel each other at all before they touch each other.
But so far there is no dynamics. So you just put this.
Yes, dynamic starts when I hit one, for instance, sphere, and so then this sphere hits another. This sphere hits another. So the first sphere, which would be which I hit, it would be in red in this picture on the left, but all the rest would be blue. Then it hits the other, and there would be two red spheres who move, just move, and then these two start hitting more and more, and the number of spheres which I hit, increases. And so these reds are all which are moving and after some long time t. In principle, it could be somewhere inside if you have a bigger and bigger simulations. For instance, somewhere on in the north west, you can see, for instance, 3 blue inside. It could be, a little bit some tiny lakes of spheres which are not yet hit even inside it. But generally, it's actually more or less everybody inside.
And the flux, the energy flux is constant, or it is just an impulse?
The energy, there is no energy flux apart from the very first hit. I hit the first particle, and for instance, suppose its mass is equal to 2, velocity is equal to 1, so energy is equal to 1. It's forever in the system, the energy is equal to 1, but it's equidistributed by more and more particles.
Okay, thank you.
Okay, so that is what I call a high school framework. Yeah, I still think it's a high school framework. And for instance, here a few groups which studied it after mentioned. For instance, one is in Paris area, Orsay group, Trizak and his friends. Another is in India, Rajesh, and actually it's not just up 2021, they still keep publishing papers. Yeah, and those guys studied this problem, and they also studied, some generalization. For instance, they assume, considered what happened if collisions are inelastic. Anyway, so when I got to that problem back, I was surprised, because before, when I was like a student, it was always, we were always told that problem arose. That problem arose when people studied atomic explosion, and yes, but now it's much more popular in astrophysics, and probably over there it's closer even analog of that problem. During the supernova explosion. So anyway, so in that case, it's really, as you asked initially, what the energy, this energy somehow released is immense. It's totally immense, and because of that, the zero temperature approximation is particularly reasonable. And also the gas is essentially an monatomic, as in our case, the gas of hot spheres. Yeah, so anyway, so all this work in astrophysics, in work in 40s about atomic explosion, relied on continuum approximation, on hydrodynamics. And so one of the kind of bigger goal here is to see how this hydrodynamic approximation is it correct or not. And actually, we are close to the regime where some problems can arise, because system is at zero temperature. Definitely, there is absolutely no equilibrium for this, particles or these spheres in initial state. They at zero temperature, they just stay still. But this system, especially for hot spheres, is also well suited for direct microdynamic simulations. And so we can try to do it, and we did it. Yeah. Okay, so that is a thing, and so how you approach this problem? So somehow, what is main, maybe chief message, at least from all previous work. So you think about it that you release energy. In our case, it's just one particle. It suffices, yeah. But typically in this cases in nature or in technology with nuclear weapons, you release a huge amount of energy in a very small region. And what happens is that it creates a spherical shock wave, which propagating through the gas, which is not moving. And so this problem is can be solved, and it was solved in the continuum, at least approximation, in the case when the pressure behind the shock it can be neglected. So atmospheric pressure is, for instance, if you talk about atomic explosion, is very small compared to the pressure after the shock. Yeah, and in normal condition, it was never valid for somehow normal explosion like normal bomb, but with atomic bomb it was valid for a certain time, maybe up to the explosion propagates for maybe a few kilometers. But at zero temperature gas, it remains valid forever. So this infinite strong blast approximation is not approximation, it's forever true. We do not need, for instance, to kick the very first particle with very high velocity. Not at all. It's totally irrelevant. We can hit it with a minute velocity, but it's still infinitely strong compared to the zeroth velocities. So it's actually really in that case, if for instance continuum approximation is correct, it would be provide provide great result, exact result forever, not for some small time before the temperature behind the shock becomes comparable with not temperature, pressure behind the shock with atmospheric pressure, but forever. Okay, so if this is true, so how it was, you can try to analyze it. And it was analyzed originally. So people say that, okay, you release certain energy E. Then you have certain density phi away, and it would be uniform for the shock, rho infinity. And there is a time. And so you think that there are no other parameters. If it was pressure was important, P infinity, it would be impossible to find solution from dimensional analysis. But if you say that the shock is infinitely strong, and in our case pressure is identically zero because zero temperature, there's no other parameters. So you just think, what kind of distance from dimensional argument follows. And the only possibility is energy times what's written here, energy times squared divided by density and power 1 over d plus 2. And so if d equal to 3, you get, this scaling time to the power 2/5. And if d is equal to 2, as in our case in simulations was, you get t to the 1/2. So, everything is determined without any effort, apart from the amplitude. And amplitude, I put it just inside. It doesn't matter. I can put in front of this formula. That's something dimensional number. And that number to compute requires more effort. Some, few details, yeah. So so this formula, this really simple and beautiful formula, it works if we somehow trust continuum approximation, and also if we consider an infinitely strong blast. And in our case, infinitely strong blast remains valid forever. It's not so clear, this formula, if we somehow switch framework to microscopic. Essentially, people never did it, for years, but in our case, it's just very natural. We really somehow thought about it almost like billiard system. And so apart from those things, which I mentioned, energy, time, density, there is also some microscopic length scale. For instance, in one dimension, this formula, I put d equal 1, and I get energy times time squared divided by density to the power 1/3. Okay, that's okay. But there is also a length scale, is just typical distance between adjacent particles. So in higher dimensions, we can also use this length scale, or we can use also diameter of spheres. So there is some microscopic scale, and it's not clear, initially why it disappears, but it does. But it turns out that we are lucky here, and in, for instance, other problem which I mentioned, which is splash problem, those other scales do not disappear. And even in this problem, if you consider more deeply, I would argue that it's actually this more intrinsic length scale, microscopic, do not disappear when you consider somehow a little bit deeper. Okay, so a little bit of a history. So in this atomic explosion, it was this formula which I wrote first, like T to the power 2 divided by D plus 2. So it was from dimensional analysis envisioned by Jeffrey Taylor, one of the greatest hydrodynamists on the left, and then, John von Neumann in the center. Essentially, it's the very same day. I guess it's the very same day, but Taylor was in England and von Neumann was in Los Alamos in US. And von Neumann was very competitive, and he learned that Taylor did it, because they exchanged, it was just internal reports. Had the same thing as he got apparently very displeased with that and worked hardly throughout the weekend and found exact solution. And then also Sedov found exact solution in like 5 years later. But then, spent a lot of his career, claiming that he was the first. Because those guys, their solution, for instance, von Neumann was published, somehow in open press, much later, even after his death. Okay, there are also quite a few more people and really brilliant people. For instance, here, if you go from right to left, you have Hans Bethe, a really brilliant physicist, another brilliant physicist, Rudolf Peierls, and then Klaus Fuchs. And Klaus Fuchs was first, assistant of Peierls, and then worked, from England, moved to US in Los Alamos, and worked under more or less supervision of Bethe. And for instance, they use this solution, for strong explosion, but mostly they considered it kind of inside, this close to the place where explosion happened, what is the temperature, and so they consider different continuum approximation after that, using, some radiation transfer, whichever. And so, for instance, he wrote some papers with Bethe and with von Neumann. Yeah, but of course he mostly known not for that work about strong explosion, but because he was the best Soviet spy, and so he really transferred a lot of secret. But I guess not about that problem, how to make this nuclear weapons. Yeah, then spent, I guess, okay, I read a little bit about him on Wikipedia. Spent, I guess, quite comfortable, maybe 5 years in American prison. And then he was released, and he went to German Democratic Republic and was a big scientific boss. Yeah, so now in Wikipedia it's written that he was idealist, but I guess so he gave all the secrets to Beria and others without money, just because he thought it's the right thing to do. But okay, we probably now think a little different. Okay, so forget about now history, and let's just very few equations. So how you treat this problem? You say that it's really simple, and generally a lot of problems in aerodynamics and sort of compressible, but are simpler than when you consider incompressible. So you have really region, one is behind the shock and one outside. And outside is trivial, there is nothing else. There is velocity equal to 0, everything. Here, because shock wave, because this motion is radial, so there are just 3 variables, one variable velocity radial, and there are 2 variables which are thermodynamic variables. For instance, here I took, density and pressure. And so first equation is, on the top is just continuity equation, mass conservation in radial case. Equation at the bottom is Euler equation, and equation in the middle, sometimes you call it entropy equation or energy equation. So that's only involves something else, and it involves this diabatic index. And that is in the realm of compressible and generally hydrodynamics is just somehow something which you should get from experiment or whichever, you don't know what it is. But here kinetic theory comes, to help. And for instance, if you have monoatomic gas, but a dilute monoatomic gas, so this gamma is 1 plus 2 over d. Yeah, I say dilute because if it's not dilute, you do not even know the equation of state. Yes, so that's a kind of where we are. For instance, when we have, the simplest possible imaginable system of hot sphere gas, we do not know its equilibrium, when the occupied volume is sufficiently big. So it's only when it's dilute. Okay, so what you do after that is really simple. You just use essentially dimensional analysis still. Velocity, the only dimensional things are divided by t times some function. Density is just rho infinity. And for instance, p divided by rho, temperature is what I wrote here, the third one. And it can depend, just this function, capital, can depend on some separately on distance and time. It's actually depend on scale variable, psi, which is r divided by r, capital R. And this capital R, we know that it grows like t to the 2/5 in 3 dimensions, so 1/3 in 1 dimension. And so you just plug this and that's which on the top in this equation from the previous slide, and you get 3 nonlinear coupled ordinary differential equations. And that equations, again, when I was student, I saw in books they just give you solution, but essentially nowhere solution is described in details, and that's what was found by von Neumann and by Sedov. But it's always in 3D and for arbitrary gamma. And so when actually I said, I got back to that problem, and Abhishek wrote to me, so actually I just did it myself for this, and in one-dimensional case, I solved it. I solved the same what they did, and it was really surprising. Kind of, I just was shocking to me that 3 coupled to DE nonlinear can be solved, but they can. And so I found solution, and in particular, I found this amplitude A in 1 dimension because they were simulated 1D, and so this amplitude A turns out to be that number. Yeah, kind of that problem becomes a bit, famous for kind of general public. And also, if you give a talk about it, you just, a little boring because I described it many times, but you have to describe the story. The story is the following. So in 1950s, US published the photo of this explosion, and they said that, it was, this, mushroom sort of, cloud, and so it was that it was reached, shock wave distance like I forgot 1.5 miles or something after like a certain amount of second, and then Taylor, he somehow just released, in few days, what is the energy, and the energy was absolute secret. So how he did it? He used this formula is at the bottom, but in that formula was not 1/3 but 1/1/5 exponent because it was in 3 dimensions. So he just pick up what they showed, r this 1.5 miles or something to the power 5, and then multiply by density and divided by t squared. And so he estimated energy, and it was extremely close to the actual value. But, if Taylor would have lived in, or we lived in 1D, so in that case, his energy would be 1/7 times smaller than actually 1 divided by 7 of actual energy, because this amplitude, you see, is, equal close to 7. But in 1D, in 3D, it just happens to be, and also in air, where gamma is 7/5, is this amplitude very close to 1. So it was luck. Okay, so what we actually do, at least in this first walk, where I got back to that problem. So this Indian, my collaborators, they just decided to look at 1D. And in 1D, it's actually very pathological, because if particles, as I always consider, assume in 2D and 3D have equal masses, they just exchange velocity. So if, for instance, I hit one particle, it just hit, for instance, to the right, it hits, next particle and stops, the other moves, hits next and stop, and so there is absolutely no phenomena which I described. But you can very easily get the same phenomenology if you introduce some mass dispersity. And they just consider the most trivial one alternating hot particles. So the particles of mass like 1, 2, 1, 2, 1, 2, 1, 2, and it is enough. Really strange, but it is enough. So you actually overcome this one-dimensional pathology. And so that's what they consider. But studied because 1D easy to study numerically, so in great details, and we found very good agreement with this TVNS, Taylor von Neumann-Sedov solution. But okay, our version one-dimensional, which I mentioned above. But found actually also the most interesting we found is that there is a region also growing, but smaller than, growing a little slower than the region of the shock wave near the center, where actually you can't use, Euler equation. You have to use Navier-Stokes equation. You have to take into account this dissipative process. Also, again, no dissipation, elastic collision. Dissipative meaning that viscosity and the thing. So you have to take into account. And so we also found prediction for the size of this core region and hydrodynamics variable, and things essentially agreed with simulations. And then, okay, I mentioned that we did it in high dimensions as well. Okay, this is some of the things we just, show you that agreement between theory and between simulations is good. Shockwave position. Okay, there is no theory, for instance, for this fluctuations on the right, because hydrodynamics is deterministic theory, so that's something, but they are not large, but okay, again, more interesting results, for instance, are here in these plots. So what's happening if, for instance, if you look at the plot on the right, and if you look at the temperature, and so this, there is this exact solution, and this exact solution diverges near the origin, and in hydrodynamics you just disregard it. But you just understand that temperature can diverge because temperature can be bigger than temperature or energy which you initially hit particle, so it can be bigger than that. And so actually, near this region, what's happening, and how you cure this singularity, you can't use Euler equations, or you have to use Navier-Stokes equation. And so we did it, and so one of the problem was to estimate the size of this region and also to estimate solution here. Okay, so what I said before is essentially the following. So for instance, temperature near the origin from the solution in textbooks, if you wish, from this solution by von Neumann, it diverges like this in 1D, like temperature. And so that divergence is unphysical. And so how you cure it, you try to find, a lot of this contribution, which is just to estimate the contributions which are comes from viscosity and other, but basically they matter near the origin. Near the origin, just from symmetry, you realize that hydrodynamic velocity is close to zero. Exactly, the origin would be zero by symmetry. And so those storms play a smaller role, asymptotically relevant role, but the terms which do play roles are heat transfer. And so here I wrote in 1D equation for heat transfer. On the left, essentially what I called before, energy equation or entropy equation. And then on the right, I would have zero if I forget about heat transfer, but now I have this. It's a little bit more subtle here. There is still some pathology, which is, 1D still pathological. So for instance, square root of T is just how heat transfer depends on temperature, and that absolutely always happens in hot sphere gas. And okay, I'm not going to remind maybe you all details, but it's actually what we all learn in undergraduate courses, just elementary kinetic theory, because it's just proportional of this transport coefficient to the thermal velocity. And thermal velocity is like a square root of t. That's for hot sphere gas. For others could be different, yeah. But then there is some pathology which is in 1D, and in high dimensions doesn't happen. There is rho to the 1/3. So that is, kind of a lot of anomalous Fourier law, a lot of work about many people, including this my co-author Abhishek Dar. Yeah, and particularly that was advocated by Pablo Hurtado and Harido. And so you just seek the size of the region where this term becomes comparable to terms on the left, and you find very weird exponent. You find that the size, capital X here I denoted, of this region is exponent 38 divided by 93. And if you remember, in one dimension, how the position of shock waves is 2/3. So this 38 divided by 93 is obviously smaller. So this is the size of this core region, and that's the temperature of the core region. So all this exponent always 93 or sometimes 31, which is 93 divided by 3. So quite big exponent. And I guess if, for instance, you do it numerically, there is zero chance. But okay, when you somehow expect it, theoretically, numerically, you have some support. So after that, you do the very same scaling analysis as before, but inside this region, you just, use as a scale variable not psi, which is x divided by size of this where the shock waves is, x divided by capital X, eta. And then you do the very same, let me omit details, and you get equation for instance, for the temperature, scaled temperature, capital F. And equation is non-linear, but now our luck at least round out, so you can solve this equation analytically, but numerically you can, and you see something like that, so it doesn't diverge at the origin. And the velocity, for instance, this velocity more or less blue is where you take into account this dissipative effect, and that what would be, it was strictly linear if you do not take them into account. Okay, so more interesting, at least from physics point of view, because 1D is a bit pathological. Yes, if you work in 1D, like some people, in statistical physics, you try to see anomalous Fourier law. It was popular and still popular last 20 years, but still kind of, from general point of view, 2D, 3D seems much more sane. And so if you're in 2D and 3D, you do okay, strictly speaking, you can't even solve Euler equation in that case, because if you have, as I said, if you have your particle should have some finite size, otherwise they in 2D and 3D they would never touch each other, and it would be no relaxation. So they must have final size, and so they must occupy some volume fraction. And if this volume fraction is, for instance, 0.3, you do not know, and generally for any formally positive, you do not know equation of state. And it becomes closer and closer to ideal gas only when this volume fraction goes to 0. So essentially results, and you can rely on kind of solutions of Euler equations, this Taylor von Neumann Sedov solution only in that limit. That's one comment. But okay, so we rely on it. We rely on it, and so but in simulation sometimes we have a volume fraction 0.3, but typically we take it small point because evolution is faster, but typically we take it small. So another thing which is also kind of, you just switch framework from continuum to discrete, and you just see a lot of things which you take for granted are kind of questionable. If, for instance, again, size becomes equal to 0, it's actually definitely the first particle you kick propagates without touching anybody forever. And so there is no this phenomenology. And if this volume fraction is 0.1 or 0.01 or 0.001, it's just just one weird that actually position of shock wave in very long time limit totally doesn't depend on this 0.1 or 0.01, you know, and that is, you know, a mystery, almost a mystery. So it really tells you that, you know, that thing is important because it's really triggers the system. It's you have to have it a little bit small, but after that it's just irrelevant. So anyway, so but when we repeat all the analysis which I more or less described in outline, not described in 1D. So you do, for instance, you find in 2 dimensions, you find actually the size of this core region. I call it here H is 2/5. And in 3 dimensions, size is 62 divided by 175. Generally, in 2 dimensions, all the things are sort of normal. Exponent, not normal, but exponent. You see, for instance, density decays in this core region. I wrote 0, meaning origin, but it's more or less uniform in this core region. Is like T minus 1/5 and temperature T minus 4/5. But in 3D, you see quite weird exponents. Yeah, and in 2D, we confirm it. Exponents, you know. So, okay. So, okay, that's essentially, you know, I can talk more and could have talked more and give plots like in 1D because we worked, you know, in details in 2D, but let me drop it and let me consider something new or more new. So, for instance, one thing which I kind of physicist, at least most of us, and at least in the past, you know, like 100 years ago, physicists knew hydrodynamics. Okay, I just happened to be, you know, as a student, you know, really had courses, but most physicists don't know much hydrodynamics. Even now, it's a bit more popular because of generalized hydrodynamics, because it becomes popular in quantum realm. But that's a little bit, you know, for us, a little bit, you know, outside of what we typically know. And so you say that, okay, there is this region, core region, where for instance, dissipative effect matters, but little hard. Maybe, you know, because maybe most of you never work seriously with any Navier-Stokes equation, but we can forget about it and can actually look from the totally point of view, totally, again, you know, almost high school point of view. So just look at that. Of course, it's just illustration and badly done, but still, you know. So I have the very same system, and I just draw with the blue, you know, stationary balls and with the red moving balls. And there is one which is black, and black is the very first which I kicked. And so it's definitely one of the moving inside this region behind shock wave. But then I ask where it is actually, where it is, you know. So what is kind of typical fluctuations, typical position? Is it really close to, could be close to the edge, to the shock wave or not? And the answer is not. And the answer is that it's actually essentially inside this core. So how I do it, okay, a little maybe long, but first you forget, you say that, forget about this setting and you remember something you know better, Lorentz gas, where your kicked particle is actually has 0 mass, and so it doesn't affect others. And in that case, you introduce, for instance, mean free path, which is again some very basic thing for undergraduate physics, essentially. And then you say that there is diffusion coefficient, which can be just nothing even from dimensional analysis, like mean free path times velocity. And then you say that this particle would propagate diffusively like root of dt. And you do the very same here, but now, of course, not of course, but yeah, now this velocity of this, you know, impurity becomes smaller, and so you try to really to find, just presume that it's within certain range, and just try to find that it would be agree with that estimate where d is, you know, kind of take into account that velocity becomes smaller. And after a lot of this thing, you find that impurity position, typical, this is written equality, but don't take it very seriously, typical scales like that for arbitrary dimension, dimension bigger than 1. So an impurity velocity scales like, you know, second formula. And then, you know, you just realize that it's exactly this R impurity is essentially typical R impurity, position of impurity is like the size of my core region, and V impurity is just square root of temperature in this core region. So that's what you find, yeah. And so this is again essentially the same, you know, which I had before. this kind of table, but rewritten in terms of impurity. So in 2 dimensions, for instance, impurity t to the 2/5 and typical position, and in 3 dimensions 62 exponent over 175. Yeah, so far so good. It's still not checked. Actually, I really when I gave similar talk last time, I really thought of something interesting, and that I thought about impurity, and then worked a little more. But still, my Indian collaborators are slow, so they still didn't check it numerically. But this is if you like such problems, you can immediately try to somehow to do something more, because that's just dimensional, not dimensional, because dimension gives you there are many dimensional length here, but it's still sort of scaling argument, sort of heuristic. Also, I think it's not heuristic, it's really provide you right scales, but you want to find more. You want to find position distribution, you want to find velocity distribution, you want to maybe find even joint distribution of position and velocity. And you probably want to find first two, but the truth is here that very often, and okay, I wouldn't go now because I'm now still have a bit to describe, I guess, yeah. But in many such problems, the only way to proceed, you have to find first joint distribution and then integrate it to find separate distributions. And it's not so clear even the framework of this. For instance, here in my arguments, here I use the diffusion arguments, and so you may try to write for this PRT diffusion equation. And then properly put, but what to put the diffusion coefficient? If you just put a time dependent just from this average thing, yes, it would give you estimate of R of the order of t to the 2/5. But then you consider that actually there is a still convective term, because fluid here moving radially, and if you take into account convective term, they are smaller velocity, hydrodynamic velocity, but they just go in the one direction. It's just and so it actually they provide the same contribution. So, but I still don't know, can one just rely on a convection diffusion equation with somehow velocity and the particular diffusion coefficient taken for velocity? I guess I can take as a function of R of t because I know it. So it's actually a very basic problem, I guess, just to find PRT and unknown solution. Okay, maybe now another thing which actually I thought more recently, and partially even because of this talk, and I thought that maybe I'll write up something, but still didn't write up something. So it's actually something which is called bow shock. And as a strong, this explosion is now much more popular in astrophysics. Okay, with, for instance, the most main application to supernova. This supernova is of course wonderful. Yeah, for instance, I've read, I don't know why, they claim that almost always explosion takes 100 seconds. And so 100 seconds is immensely instantaneous because scale are immensely huge. And bow shock, they originally in hydrodynamics, so typically you have object here written as shown as red, and it moves through the medium and moves with supersonic velocity. And so this what I draw here, kind of boundary, moving boundary would be sort of shock wave. In front of it, it's sort of standard, and then it becoming, far away becomes, somehow very big shock wave and propagates with angle. Inclination would be arc sine of 1 over Mach number. But imagine that you have hypersonic, not just hypersonic, but but infinitely strong, so somehow moving with Mach number infinity. So it tells you that actually its inclination becomes equal to 0, but it should be growing still. And so how? And so again, now recently it was some work about it in astrophysics, and what they were arguing is that if you go very, very far away, behind this, so what you have is a strong explosion, and in this case would be infinitely strong explosion, and it just grows in this vertical direction. Yeah, so dimension is 1 unit smaller. And so if you do that, which is really not fully proven, but seems, you think about it, totally correct argument intuitively. So you find that in 3D, for instance, you find that because in 3D, because here dimension 1 unit smaller, it's just propagates like root of t, and this position to this point is t, so it's actually propagate like parabola. It's actually the shape of this thing is parabola, square root of x, y equals square root of x, and then in 2D it would be x to the 2/3. But I'd like to kind of think in this very toy my setting which I use here, more details, and also to think a little bit about this core region which would be here as well. And I can just use my previous result, because now I have to use gamma corresponding in two-dimensional case to 2D but not to 1D. So it requires some think, and also thinking about this place here where this core region, so it's kind of funny. But anyway, so this bow shock are extremely popular in astrophysics, and for instance our Earth, there is solar wind, and also for all other sorts of objects, and that would be our Earth moves within this with a very strong hypersonic velocity. So it would be a bit similar to what you have here. Also, it's more complicated in the Earth case, because there is also effect of electricity, because Earth is magnetized. And for instance, for a few other planets which are not magnetized, it would be closer to this. Okay, so now let me talk about some, I have very little time, about some, in a way, more paradoxical semi-infinite system. I just, consider that half space is occupied initially, and I just hit with one particle. So not exactly that, but some what similar problem was studied, but with continuum approximation by two other guys, which were influential in this important in that atomic project. One was really important, Zeldovich. Another, von Weizsäcker, was a friend of Heisenberg. So okay, they fortunately didn't succeed in building a nuclear bomb. Yeah, but okay, they worked about it not during this explosion, much later in 50s. And actually, more or less, this picture was actually, I learned it recently, was introduced by Reiser. And so Reiser wrote a famous two-volume book with Zeldovich, Physics of Shock Waves and High Temperature Hydrodynamic Phenomena, where they discussed also a lot of this. Yeah. Anyway, so we consider one-dimensional version, and one-dimensional version, we have just, infinite line, and particle can move everywhere, but initially they uniformly distributed to in the half plane x bigger than 0. And the leftmost particles, for instance, x equal to 0. And we just kick it inside the system of, where the other particles. So other particles initially at rest, they're zero size, they're point particle, and they just interact elastic collision, So here is actually sort of quiz question for you, at least you think for a few seconds. Yeah, it would be much nicer if I were, it was in person, yeah. So what is the total energy of particles in the initially occupied half line? So initial energy is, for instance, equal to 1. We kick this particle at x equals 0, it goes to the x positive. And so initial energy, you just sum of energy of all particles on the right-hand side, it's equal to 1. So what it would be in long time limit? Okay, here's a question. Most people say that maybe it would be 50-50 or whichever. It actually goes to 0. And goes to 0 with very strange exponent, which is, you determine numerically with as much precision as you want. Another question. What is the total momentum of particles in the initially occupied half-line? Yes, again, without interaction is a little, a little weird to have such quiz, but anyway, so it diverges. It grows without limit as t to the power point this is, and this exponent is actually 1 minus 2 beta divided by 3, where beta is this exponent in the first answer. So it diverges. How it can diverge? It can, because on the right it's diverges and positive. On the left it's also diverges and negative. And if you sum them, it would be initial momentum, which is just 1, for instance. Yeah. So they diverges with identical amplitudes and identical, this of course exponent more importantly, and their sum is, but they diverge. What is the total number of moving particles on the left and on the right? And the answer that they both grow according to that, and they are comparable. So that is quite amusing. And if you actually look at simulations, it doesn't. So this is, dense. On the right, you see there are lots of particles moving, and on the left, you seemingly have much less. But if you divide one by the other, you get something close to 10, and you go longer and longer in time, it remains close to 10. So it remains the same. Okay, here are some plots which support what I just asked you in this quiz, so to speak. So this energy decays in initially occupied half lane algebraically with actually quite small exponents, this beta 0.11, whichever. Yeah, and for instance, momentum, it's actually diverges like this with exponent, yeah. And this R of t is actually the number of particles in it, because it's really more or less position of the shock wave, because there is still shock wave on the right. And the last plot, okay, I go, yeah, the last plot, I mean, in the down, right corner is actually the ratio of moving particles on the left to moving particle on the right. And it varies with mu. Mu is, for instance, one particle. I have alternating chain, and every second particle has mass 1, and another has mass, odd particle has mass, for instance, 1/2. Or maybe even particle has mass 1/2. So this A and B depends either the leftmost particle is heavier or light, So it depends on those things apparently, and depends on this mu, but it remains constant. So it's kind of funny that this splash problem, it actually interesting mixture of hydrodynamics and billiard behaviors. So hydrodynamics behavior happens on the right up to the position of shock wave at R of t, and on the left also in distance of the order of R of t. There's no well-defined boundary between hydro part, on the left, and splatter part. And by splatter particles, I mean particles which actually reach their ultimate speed, and then they cease to collide forever. And so the splatter particles constitute a sort of non-hydro billiard leftover. And then how you analyze the hydro behavior and also determine this exponent. So it's interesting. So essentially, you just presume that it's also scaling, and you define the very same as I was for blast problem. But the exponent depends not on little r or x divided by r, but x divided by the same r, but now with unknown exponent. And then if you do it, then you substitute it into this complicated, okay, non-linear, whichever, but still, hydrodynamic equations, without you just forget about any dissipation effects. And then you get, some system, but different from my previous problem, which was symmetric. There are different boundary conditions on the right and on the left. On the right, okay, I never mentioned it, but you have after the shock wave, boundary condition is determined by this so-called Hugoniot boundary condition, how you go through the. And so you do it, and you find that the system of ODEs, has a consistent solution only at a specific exponent value. Yeah. And so that is just fixes this B. Okay, so the splatter particles is, okay, it's called fan, typically a growing fan of which moves ballistically. And so very far on the left, its position is t, minus t, and on the right is position of this t to the power 0.62. And okay, for instance, one thing is very trivial if you kind of work on this problem, seems to be absolutely obvious, but it's sort of, sort of mathematical statement, and you want to prove it. So that each particle eventually joins the fun. So each particle eventually ceases to collide and just moves, forever. You can take particle number 77, or you can take particle number 666, or any other weird number, with religious or some other, I don't know, connections. All join it, So it's kind of very bold conjecture and seems obviously true and perhaps very hard to prove. So before, when I started with, for instance, with this hydrodynamic approach, I just told you that macroscopic approach, you just apply, and then the only possibility that the time, for instance, in 1D, not the time, but the position of this grows like t to the 2/3. Now it's not, but why? Because actually, even not paradoxical so much, because we somehow neglect microscopic length scale, and it is here it plays a role. And actually, inside of hydrodynamics, where they do not know about microscopic, neglected, there were some things found, and they were kind of became known when your dimensional analysis doesn't fix your exponent as self-similar solution of the second kind. And so in our particular case, for instance, rather than this t to the 2/3, which I had before, we can have, still scaling of the unit of length. We just write time to the power 2 minus beta divided by 3 times length to the power beta over 3. Length is just the distance between interparticle distance. And so that's dimensionally correct. And in kind of macroscopic, you just do not know how to invent this length, but here it's just in your face. And there is also a remarkable analogy, not as much known as it probably would be good, between the self-similar solution normal of the first kind and self-similar solution of the second kind. It's actually what we use without using that language when we describe phase transitions. So sort of first kind is kind of Landau, kind of mean field, and second kind is kind of Wilson. And that point of view is the only place really emphasized, but a lot by Goldenfeld in his book, already now 30 years old, I guess, lectures on phase transition and the RG. Okay, so I don't know how much I have. Okay, if you want a few more minutes. I started.
You still have 15 minutes.
15. Oh, okay. I thought that there are questions. Yeah. In that case, okay, I guess I really.
They might be at the end. So
Yeah.
save a little bit time for questions.
Yeah. So not too much remains. Yeah. So I started with really simple and one, I guess, good problem, which is, still has no answer. And actually, you will see it's tiny bit related to what I'm about to say. So you have a finite number of balls in d dimensions. How many collisions, maximal collisions, they can undergo? Because after a while, they just form fan, but not like in my case in 1D, but, so they never collide again. So Sinai conjectured in the late 60s that the number of collisions is always finite, and you think about it and it seems obvious, and nobody come up with a proof, so eventually he proved himself this conjecture, but only in 1D. And then his student Wasserstein, I guess he has some famous Wasserstein metrics or something, proved it's in arbitrary dimension. But the problem remained very popular because what they found maybe this people were finding upper bounds, and they bounds are immensely far from the tide. But for instance, if you want to know exact number, you can call it Sinai number, whichever maximal number of collisions. SOB, where we have b balls, depends also on dimension. And in 2D, not in 2D, for 2 balls, obviously just one collision. S of 2 is equal 1. For 3, as I told you, very long proof of this Murphy and Cohen, that it's equal to 4 maximal, and for 4 balls, it's unknown. And so here are the best bounds, known bound. Okay, they're a little bit now more precise, but essentially I put main chief features. One is n squared, a lower bound and upper bound immensely large, n to the power n squared. Okay, in my case, in our case, okay, we back to 1D. So you just understand the size of the system and walk a little bit more, and you just see that the number of collisions ought to scale as this t to the power 2 minus beta divided by 3. And the dominant contribution comes, of course, from hydrodynamic region, and actually, you know, the splatter region, strictly defined splatter region, where they stopped colliding, so it has zero contribution. But okay, so that is growing, that's clear. But if you pick up every special particles, you know, so is it possible that it keeps colliding back and forth ad infinitum? You know, so the analog of Sinai conjecture, I would say, in splash problem is no. Each particle, whichever you prefer to take this particle number 77 or 666, it undergoes a finite number of collisions, you know. So, but to prove it, it's hard. But okay, even, you know, it's actually even worse things happening. For instance, you consider, not worse, but kind of less is known. You consider the leftmost particle. So again, you have a system, infinitely many particles, but initially occupying half line, one dimension, yeah. And the leftmost particle, you just hit into the right, you know. And so the question is how many collisions it may undergo. So here is kind of written the number of collisions for this left moving particles. So I assume that its mass is equal to mu, and it's alternating system, and the next particle has mass 1, then again mu, then again 1, and so on and so forth. So this is, you see, conjectural actually thing. From when mu less than 1, it's just one collision. So if it's more light, it just hit it, a more heavy particle go to the left, and it would be never caught again. For mu bigger than 1, but up to certain mu critical, it would be 2 collisions, and so on and so forth. But is it true? Is it really that universal picture doesn't depend on the initial location of this particle on the right? Not known, not known. And even less is even not known. Is it true that when mu is less than 1, there is just one collision? It's just amusing. I find it amusing. Really, you know, you need to know nothing, you know, to see this and how to prove it. And I discussed it with a few, quite a few people, you know. Some even were very good mathematicians, you know. So nobody, at least, you know, seemingly has a clue how to prove it. So for instance, I have this alternating mu1, mu1, mu1. I repeat what I'm saying. And initial velocity, the most left particle has velocity 1, others are 0. When they collide, there is this v1 and v2 is just, you know, follows from elastic collisions of this point. You know, and so when mu is less than 1, v1 is negative, it goes to the right. And then, you know, the best I know is the following. So this you have velocity after first collision of the second particle. And then you just think and you realize that, at least I think you would realize that its ultimate speed, after maybe it undergoes a few more collisions, it can be bigger speed, so bigger than this, you know. So it becomes negative eventually, but can be bigger than that. And so I just say that, okay, when it happens that v1 minus v1, because v1 is negative, bigger than this, you know. And this happens for sure when mu is less than 1/3. So this conjecture, which I plot here, if mu is less than 1/3, it's true. It's really the first particle undergoes one collision. But if mu is, I don't know, 1/2. Yeah, I guess it's true. And perhaps the proof is, ultimate proof is almost trivial, almost like few lines as I proved to 1/3. Yeah. Okay, so a few more things. For instance, I told you that the energy, this is W's are splatter final energies of the particles on the left, you know. And I told you that they constitute essentially all, asymptotically all energy in the system. So if I sum them, okay, I should of course multiply one by some of them by 1, another by mu, but it's sum is should remain of order 1. Yeah, that's clear. And then I also told you that momentum is actually diverges like that. So I have these two sum rules. So one sum rule is just, you know, even you can put it up to infinity, is a convergent sum of W squared. Another is divergent. And so if you just presume that it goes like e to minus some power, and you know how much you have to sum, upper limit, this I. So you get, this minus some power is equal 1 plus beta divided by 2 minus beta. Again, it's universal. It doesn't depend on mu, for instance, on this mass ratio, but, exponent. And yes, so simulations confirm it. Okay, so let me now more or less come to the summary. Yeah. The agreement between direct molecular dynamic simulation and theory seems actually better in one dimension, which is a bit pathological. Okay, we just fight this pathology distributed masses, then in 2 and 3 dimensions. So hard to 100% to say what causes it. So actually it's good agreement in 2 and 3 dimensions, and initial studies were sometimes found better agreement in 2, or better agreement in 3. Now it's actually quite good, but not as perfect. Also, this my Indian co-authors, they informed me recently that they found some bug in some of the code, and so now agreement in 2D mostly. They studied 2D is even better, is close to perfect. Yeah. For instance, where it is disagreement, at least with compressible aerodynamics, so without viscosity, without this transport coefficient, is bad, as we found in the core region. But also it's bad, which I didn't discuss here much, close to the shock wave in the realm of like compressible hydrodynamics is just discontinuity of the first kind, so to speak. Yeah. But inside shock waves, we can formally, at least if you want to find that structure, we should use Boltzmann equation. Boltzmann equation, even in a simpler framework, is just constantly moving shock wave, never was solved for shock wave. So Boltzmann equation is extremely difficult. And actually, first attempt to solve Boltzmann equation was also made by somebody, and famous somebody, Igor Tamm, Nobel Prize winner, during the work on the atomic bomb project, but it was some uncontrolled approximation he used. So the blast and splash problem is actually not the best setting, and so we didn't pursue it, because it's better to consider, for instance, piston problem, where, for instance, you have half space occupied and have infinitely heavy on the left, and it's just suddenly starts moving to the right. So it's just would be nice. What could be easier than exact solution for the shock wave? For the really not, as in our case, shock wave actually moves with velocity non-constant, but in simpler case, and the piston constant. And it's just Boltzmann equation is extremely hard equation. Would be really good to study that for sure. Another thing also, the very first plot I showed you, you see that actually the surface is not strictly spherical. And at least in statistical physics, we love last maybe now even 40 years, really surface fluctuations, for instance, KPZ kind of things, So what here are these fluctuations? Unknown. And they're beyond the scope of deterministic hydrodynamics. And at least numerically, it's also hard. Even I urge these collaborators infinitely more capable in numerics, but they didn't do much simulation. It seems that actually these fluctuations are small, not like in KPZ, something like T1 third or something, growing with maybe logarithmically growing, not known yet. Also, in the splash problem, find this limit shape of this thing is, but in 2D, in 3D, totally unknown, and I guess it's extremely hard problem. Extremely hard. I do not see at all, how even to start doing it. And okay, for instance, also I was talking about the splash problem, where the most trivial the most basic questions about leftmost particles still not answered. Okay, so thanks a lot for your attention.
And thanks a lot for your nice and very rich talk, and maybe some questions or comments. Are there any?
May I?
No, of course.
Thank you. Thank you very much, Pavel. Very nice indeed, and very physical and very mathematical. I don't know how to say. Two questions. The first one is the following. As you know, many physical problems become trivial when you have high enough dimensionality. For example, self-avoiding walk starts to be, forgets that it is self-avoiding walk and starts to behave as a random walk when dimensionality of space is larger than 4. What would you say? Could one expect something like upper critical dimension for your problem? When something becomes, when all these scaling laws become trivial?
A kind of mean field we
Yeah.
have.
Yeah.
Close to my heart question, so I don't feel that it would be here any upper critical dimension, but absolutely true. Large dimension often helps you. Yeah, and here there is no like somehow phase transition like in self-avoiding walk, but things should be simpler. And for instance, one of the most beautiful things, at least in my mind, I really love it. I mentioned a very basic problem, equilibrium. Hot sphere gas. So it's actually known in 1D. Tong's gas, it's totally unknown equation of state in 2D, but in very high dimensions, beautiful work by Harry Frisch and others. They found equation of state, and it's essentially like van der Waals gas for the finite volume fraction. There is maybe phase transition after that, and maybe it's actually people still discuss that, liquid, gas, whichever. So it's a little different because I always here consider dilute system, but it's beautiful thing. And also Harry Frisch tried, and I'm not sure any people continued it, I guess, with Ilskens, another very good scientist from France, I guess. Yeah, Harry Frisch is from Albany, and so they tried to do something for Boltzmann equation in high dimensions, and limit of very, very high dimensions. And so that's really perspective thing. And for instance, maybe closer again, not some phase transition, but closer to answer your question is, for instance, by very, very famous guys and his students and collaborators and friends, Parisi. And one of the things they did recently, they wrote a book, simple liquid or something in infinite dimensions, and they have a lot of exact result in infinite. So basically, the idea that you have somehow you go away from ideal gas and more like a dense thing, and yes, things become simpler. And I guess it's unexploited, really, try to do it in Boltzmann framework, whichever. So yeah, it's you just step on my wound, which I love.
Sorry, sorry for that.
I love to kind of to explore.
Sorry for that. Thank you. And then I don't want to step on another wound, but another question. What if you have you thought about introducing damping to your system?
No, I like the fact that it's totally ideal. So no, I actually, okay, maybe none of you asked, but I actually also liked, for instance, to consider system where particle would be a point but still interacting, and so I can do it even on high dimensions, but point particle. And so with point particle, I'm more like at least believe into the equation of state ideal, but they should interact, otherwise they wouldn't scatter. And so they can interact, for instance, like Maxwell, molecules, like potential 1 over r to the power 4, I guess, in
Lennard-Jones, maybe.
Lennard-Jones harder. It's more realistic. You're absolutely right, but it's harder. But this is just this, and in that case, for instance, all these laws which I plot, like t to the 2/5 and something, I can generalize. But the bad point that actually systems, even they initially stationary, but they start moving. So somehow I have to use it only up to certain threshold, and then say that there is no interaction, because I want those particles outside to be still stationary. And so here is a little bit, less clean framework, but all the exponent change, and it's some of these things, yeah. But I like more your suggestions about infinity.
Okay, thank you.
Are there any comments, questions?
Yes, we have a question from Josip Humenuk, please. Unmute yourself. Turn on your microphone, please.
Okay. Thank you for your lecture. I would like to say what changes if you add potential of interaction to your point particles. But
So that's exactly what I was starting to tell to Yuri, even he didn't ask it. It's exactly, I tried it. We tried it, yeah. And so we say that particles in that case is actually better because we can consider in some sense particles, point particles, and we just add potential. And different from kind of more realistic Leonard-Jones, we just take potential, which is purely algebraic, 1 over r to the power nu. And for instance, that potential are famous, maybe not very much known outside, but in Boltzmann equation. And so when nu is equal in 3d4 potential, in that case, it's they called Maxwell molecules. Also, they are actually atoms. And that's the only case where, for instance, transport coefficient were computed. You know, and Boltzmann tried unbelievably hard to compute transport coefficient for hot sphere gas, but apart from scaling proportional to root of time, he couldn't compute amplitudes. Yeah, and so some people claim that he killed himself because of that, because he's like 30 years of effort, you know, without success. So Maxwell molecules beautiful. There are a book about it. At least there are, yeah, beautiful. Whoever met them, they like them. But here a little bit what is bad in my framework. I really like the rest behind the shock wave being stationary. And if I have this 1 over r to the nu forever potential, they start, you know, actually affecting each other. It's almost like in cosmology, they interact and they start moving. You know, so I guess it's more or less important this r minus nu nearby, and if they say we have this potential and then suddenly becomes equal to 0, almost like with Leonard-Jones, but with this Leonard-Jones path, you know, just being equal to 0 potential after certain big radius. And so if the density is small enough, it seems working. And so it changes, definitely doesn't change non-dissipative path. This equation totally the same. There's absolutely no change. But this core region becomes different. But in 1D also, yeah, this is just totally, you can try to do something in 1D as well. You know, we didn't try with interaction. Yeah, so here actually, yeah, great. Thing because you really ask the most basic questions and you don't know answers.
is it possible to add a square well interaction, a square well attraction to the point, hard point particles? A square well attraction.
So I have an answer to this. Do you see it?
Okay, thank
That's
you.
a very good. May I ask you?
Yeah.
Could we get back to the very beginning? I mean, get back. I just want to realize the microscopic picture of the blast model. So you have a space filled in with some infinite number of quiescent disks or balls, right? And then you put inside some number, finite or infinite, I guess finite, number of moving balls. And they collide with they wake up the quiescent balls. Is it correct?
Absolutely, absolutely. So, but the funny thing that it's enough. Okay, I even don't put them inside. I just kick one of them, and just one is enough. You kick it in certain direction, and it seems that you introduce actually directionality of the problem, but it's asymptotically relevant. It becomes isotropic. But for instance, these friends of mine, Indian collaborators, they prefer your framework, and they typically hit not one but like 10 particles, and then you know in small region. And they actually also kind of ensure that momentum is equal to 0. So for particles, yeah.
Then
So
the dynamics is that this energy, kinetic energy, which is at the beginning, it is distributed among bigger amount of particles, So which means that they slow down because each time it shares its momentum with the other particles. Or and then I remember that you mentioned also this infinite blast.
So you're absolutely right. For instance, initially I kick one particle, energy 1. So for instance, what I have on the left, we have maybe here 10 to the 4 or 10 to the 3 particles moving. And if we just count all the energy, here mass equal to 1, count all v squared over 2 of all these particles, we still get 1. For instance, this formula shows you that that this r goes like t to the 2/5 in 3 dimensions, and if you differentiate this formula, you get this shock wave propagates with velocity v t to the minus 3/5. So it's actually propagates slower, exactly as you're saying, you know, exactly. Volume becomes bigger and bigger, but propagates slower, because if it propagates with velocity like 1 initial velocity, so you would have a lot of these particles on the boundary, and the energy would be much bigger than initial one. So exactly, you have right intuition, yeah.
And so one more, if you allow.
Absolutely.
So could I replace this model with the following one? So you have distributed point particles, but each of them has some halo around. And then some particles start moving, and then when they reach this halo, they just exchange their momenta. So each particle is described by its position and momentum.
Yep.
And then within this collision, they change their momenta,
Yeah,
and start moving. So is it more or less the same model?
I guess the same. I guess you know what you call hollow is just the radii of my disks. Yeah, I guess the
They
same.
are all disks.
Yeah, I guess the same.
Maybe the same. But I'm trying to translate this to a microscopic model and to start writing its dynamics. And the whole system is infinite.
Absolutely, infinite. Absolutely, yeah.
Okay, thank you very much. It was very informative for me, instructive.
Yeah.
Maybe
I guess actually the problem is somehow scientists, we are just used to complicated problem. We just can't believe that somehow it's a high school framework at least. Yeah. You still use after that differential equation, hydrodynamics, kinetic theory to have some gamma, but it's a high school setting. Yeah.
Okay. Does anybody want to say something, because it's at the very end of the first day? Okay, if not, then let's thank both our lecturers, which we had today, for wonderful presentations. Both were, and to wish them new results.
And many thanks also for the chairpersons of today's session.
Absolutely, yeah.
We meet tomorrow using the same link at the same time. Looking forward to meeting you tomorrow all.
And have a quiet evening.
Thank you.
Quiet and easy.
Quiescent.
And before all of you,
Quiescent, not quiescent.
Not quiescent.